Alright, welcome to the Chapter 6 video for physics class. This one is going to be all about two-dimensional motion. So we're going to be taking what we learned in Chapter 5, which is two-dimensional forces, and applying it to see how objects will move when they experience forces in both dimensions at the same time. And it's going to be kind of cool because now we're going to have stuff, instead of just moving in straight lines, it's going to start to move along curved paths. So here we go. There's three types of things we're going to examine in this video and in Chapter 6 from the textbook. First one is projectiles, which is launching stuff through the air. Second is circular motion. There's a whole bunch of examples of circular motion that we can talk about. And then the third is relative motion. So if you've ever gone to the airport, like this photo suggests, and you've walked on the moving tramways, or if you've gone on an escalator and then actually climbed the stairs while the escalator is moving, you know that your actual speed is a combination of both your speed relative to the object plus the relative motion of the object to the surroundings. So let's get started. First thing, projectile motion. So this is, you want to start thinking about what examples of projectile motion have you seen before, and what is actually going on physically in those situations. What are the velocities? What are the forces? What are the accelerations? How long is it in the air? How far is it traveling? How high is it going? All that kind of stuff is what you see from a physics perspective, rather than just some cannon got shot and something got hit. You know, that's what you would see from a normal perspective. So, how does the motion look? What forces are acting? In what direction are they going? So anytime you're drawing a force diagram, the two things you have to ask yourself, again to remind you, are, number one, are there any long-range forces? And of course, at this point, we've only learned about gravity, so we've got one long-range force, which is gravity. And then, are there any short-range or contact forces? And again, we're ignoring air resistance for all projectile motion. So when the object is flying through the air, it's not touching anything. So there's only one force on it, and that's going to be gravity. So the force diagram is very simple, just the object with the force of gravity pointing downward, which tells you that the acceleration is straight downward. So that means the horizontal direction, side to side, there's no accelerations, but in the vertical direction, there's an acceleration straight downward. So here's a picture of what projectile motion might look like with the velocities labeled. So obviously the object is going to go up and then come back down, but more importantly, if you look at the velocity vectors, the velocity is at an angle, right? So we're going to have to break it into components, just like in Chapter 5 we broke the force into components. In Chapter 6 we're going to be breaking velocity into x and y components. So you can use sine and cosine to do that. So, here we go. If you have the hypotenuse here, and if you know the launch angle, which would be right here, let me get a marker. If you know this launch angle right here, then you can calculate the vertical or y component and the horizontal or x component. And so as this projectile rises, it's got a downward force, right? So that means its velocity in the upward direction is going to decrease and decrease. And that's, you know this, it's slowing down as it goes up. So if you just look at the y component right here, as it moves up, the y component gets smaller. And then at the very top, this is really important, at the very top of any projectile's flight path, the y component is 0. So if it's only going straight up and straight down, its total overall velocity is 0. But if it's a projectile motion launched at an angle, it could still be moving. So it's still moving to the right. Sorry, I gotta get back in the swing of this handwriting here. It's still moving to the right, but it's not moving up or down at that moment in time. And then as it starts to fall, its acceleration is still downward. So the velocity downward starts to get larger and larger. It's accelerating downward. So this velocity vector from here to here is getting larger and larger. But in the horizontal direction, side to side, there are no forces whatsoever. So you know from Newton's first law, if the net force is 0, the acceleration is 0. And if the acceleration is 0, there's no change in velocity. So in the horizontal direction, whatever speed it started with is what speed it continues with the entire time. So this horizontal speed stays the same the entire time. Okay, so horizontally, whatever's happening horizontally, you can calculate independently of whatever's happening vertically. So for our needed variables in this problem, you're going to separate your motion, and you're going to have your vertical completely separate from your horizontal. Let me go horizontal. And of course, within your vertical and your horizontal, you have 5 things to keep track of. The same 5 things you had back in Chapter 3. You've got the initial velocity, the final velocity, the acceleration, the distance, and the time. And for vertical motion, the distance here is the height. So that's kind of nice. And for the horizontal motions, you have the same stuff, same 5 variables, but in this case, the distance is called the range. So that's just a vocabulary word that you want to make sure you know. So if they say, what's the range of this projectile motion particle, they're asking you how far it went horizontally. Time is the same in both directions. So if 5 seconds have passed in the vertical direction, 5 seconds have also passed in the horizontal direction. So time is the one variable that ties the two together. All the other ones are independent, same in both. So the time it takes for a certain event to happen is the same regardless of which axis you're looking on. However, the acceleration up and down could be different than the acceleration side to side. The height that it goes could be different than the length that it goes. And the initial and final velocities in the vertical direction could be different than the horizontal direction. So time is the only thing that's consistent across both. All the other variables will be, or could be, different. Okay, so here's a sample problem that we're going to solve. So it's going to be it's a lot of steps, but each of the steps hopefully is something you've done before because you're using the same techniques that we did in Chapter 3. A 2-kilogram cannonball is launched at a 30-degree angle with an initial speed of 15 meters per second. So right there, before you do anything else, you want to draw a little sketch/picture. 30-degree angle, 15 meters per second. So we can draw a little axis here, and we can launch our projectile at a 30-degree angle, and we can label it as 15 meters per second. Okay? Now what are we trying to find? We're trying to find, first, the components of its initial velocity. So here's our diagram. Here's the initial velocity. To get components, we need to, let me choose, I don't know, see if you guys can even notice the different colors. Let's try orange. This is going to be the x component. So I'm going to call this v initial x. And then the y component is right here. I'll call that v initial y. Okay, and this is the hypotenuse here. And this is a right angle. Because when you find vectors, you're always breaking into a right triangle. So the x component is adjacent to the angle right here. So it's going to be the hypotenuse, which is 15, times cosine, because cosine of the angle, cosine of 30 degrees, is the adjacent. Now you can use this calculator, or if you remember that cosine of 30 is root 3 over 2, you can just plug that in, 15 root 3 over 2. I'll just write that since I don't have my calculator with me. Okay, so that's my x component. And finding the initial x component is really, really important because the x component stays the same the whole time. Remember we just said the projectile is only accelerating downward. It's not accelerating side to side. So once you found the initial velocity in the horizontal direction, that velocity maintains its value for the whole problem. Okay, the y component, this side is opposite of this angle, so we've got 15 times sine 30. And if you remember that sine 30 is 1/2, this gives you 1/2 of 15 is 7.5. And oh, I need to not be a bad teacher, and I need to make sure I put my units. So this is meters per second. So the y component. So this is affecting how high it's going to go. This is also affecting how long it's going to stay in the air. The faster you launch something upward, the higher it will go, and the longer it will stay in the air. So we finished part A. We've found the components of its initial velocity. Now the question is, how long to the top and how long total? So find the time it takes to go up to the top and the time total it takes to land again. So you can imagine this projectile goes up and then it comes back down. So let me kind of just clear off some space here. So now we're trying to find the time up. So what things do we know about it? Well, we know at the beginning the vertical direction velocity is 7.5 meters per second. So if we're trying to find the time it takes to go vertically upward, we don't really care that it's moving sideways. We only care about the motion up and down. So we have that v initial in the y direction is 7.5 meters per second. How about v final, right? In the y direction. Think back to what we said a couple slides ago. When it gets to the top of its flight path, even though it could still be moving side to side, its y component will be 0. So at the top, it's stopped relative to its up and down motion, or y component. And we know the acceleration is negative 9.8 because the only force acting on it is gravity, 9.8 meters per second squared. So we have these three things. The two things that we're missing are the time to get to the top, and the distance to get to the top. That's not asked for yet, but we suspect it will probably be asked for later. So if you know VI and you know VF and you know A, how do you get T? Okay, I'm going to switch back to my other color. You can use that V final equals V initial plus acceleration times time. There's a starting formula that includes VI, VF, A, and T. Solve for T, and you get V final minus V initial divided by acceleration equals time. Okay, so now we plug in our numbers. 0 minus 7.5, 0 minus 7.5 divided by a negative 9.8. And you can see that both numbers are negative, so the time comes out positive, which is good. That makes sense. And since I don't have my calculator with me, I'm just going to put 0.75 seconds. It's going to be really close to that, 0.75 seconds. And that's not the total time, that's just the time up. So maybe I'll put a little subscript right here. So this is really important. The time that you find when you use this equation is only the time it takes to get to the top. The way that we can tell that really easily is because we used the final velocity of 0, which is the velocity at the top. So if you imagine, let me kind of finish this guy. So he's going to go up and he's going to come back down. So right here is when we have the velocity is 0 and the time is just the time to get up there. So assuming we have no air resistance, which is what we're counting on for all these problems, and also assuming that it lands at the same height that it started at, then by symmetry, the time it takes to go up this way is going to be equal to the time it takes to go down this way. And so we can say, so that's the finishing time up. Now we can look at the time total, and we can say that the total time is 2 times the time it takes to go up. So the total time should be 1.5 seconds. Again, the time up was around 0.75. Double that and you get 1.5 seconds. So that's because of symmetry. If it does not land at the same height that it started at, then you'll have to take into consideration the difference in height, and you'll have to use a different equation. But for all the problems we're going to be doing, unless you want to plan ahead for some level 3 questions on a test, in which case you should see me in office hours, we'll always have stuff land at the same height it was launched from, and so the total time will always be twice as much as it takes to get up here. So now we've got the initial and final, the initial velocity in the 2 components. We've also got the time it takes to get up to the top, and the total time. So we're almost done. How high does it go and how far does it go? Okay, obviously how high it goes is the vertical direction, and how far it goes is the horizontal. So to get the height, what variables do we know, and what variables are we trying to find? This right here, the height is actually this variable right here. So if we're looking in the vertical direction, we already know VI, VF, and A. So, and we also know T now. So there's a lot of choices on which formula you want to use. I'll just use VF squared equals VI squared plus 2AD. Because in the vertical direction we know VF, VI, and A. So distance equals VF squared minus VI squared over 2A. Again, I just subtracted VI from this side and then divided by 2A. So distance equals 0 minus V initial. Now this is incredibly important. This is where most people go wrong. When you're plugging in V initial right here, because we're solving for the height, we're only looking at the vertical component of the velocity, not the total 15. You will never use this full value 15. Once you find these 2 components, you'll never go back and use that value of 15. You're done with it. You used it to get these 2 numbers, but once you got these 2 numbers, you only use the velocities either horizontally or vertically. So the value we're plugging in for V initial is the y component here, 7.5. I can't stress that enough. That's a super common mistake. Divided by 2 times negative 9.8. Okay, I don't know what this is, to be honest. You can type this in your calculator and get the distance. It's going to be close to like, that's around 50, or maybe that's around 55, and that's around 20. So it's around 2.5, a little bit bigger, meters. I don't know exactly how far, but you can type that in your calculator. Maybe I'll make a little squiggle, so it's around 2.5 meters. Let me know if I made a terrible calculation mistake, but that's what it will be close to. And now to get the range, okay, this is also really important. To find out how far it went, since it's going at constant speed, it's not accelerating, it's going at constant speed side to side, all you have to do is distance equals velocity times time in the x direction. So it's the x component of the velocity times the total time, not just the time up, but now the total time, because we're looking from here's our starting point and here's our ending point to get that total distance, which is the range. Okay, the x component of the velocity we just said is 15 root 3 over 2. 15 root 3 over 2. And the total time was what, 1.5 seconds? So I'll put in a 1.5 right there. And I don't have a calculator again, and that's too much for me to do in my head. So you can type that in your calculator to get the final, the distance that it went. So let me summarize the three most important things in these problems. Number one, break the initial velocity into x and y components, and once you get those x and y components, you will not ever use again the total velocity. So don't plug the total velocity in anywhere except to get these two components. Okay? To find the time, you're only looking at the vertical motion. How fast it's going side to side will not affect how fast it falls. The rate that it falls is only affected by gravity and its initial velocity up or down. So to get the time, you look at the vertical motion. Once you have the time it takes to get to the top, you can double it to get the total time. And then once you have the time variables, getting the distance last is very easy because you know all other variables in the equation, and you can pretty much use any equation you want to get the distance. So I've chosen to use this one, but any of the other equations would also have worked. Okay. Last thing is check and make sure your answers seem like common sense. Like if you shoot it at a 30-degree angle, just try to picture in your head like something going at a 30-degree angle. If you get a height of 1 meter and a range of 3,000 meters, like obviously that's probably not the case. It's not impossible, but try to use common sense to check your answers. Summary. I just did this, but let's talk about it. The x and y motion are separate, so you have two sets of variables. Your acceleration, velocity, distance, and time in the x and the y are completely independent of each other, with the exception that time is the same in both. All of your equations from chapter 3 still apply. Do you remember your equations? I hope you do, but I'll write them here actually in case you forgot. So distance equals velocity initial times time plus 1/2 at squared. That one is really good. Another one is one that we used. V final, equals V initial plus at. How about V final squared equals V initial squared plus 2ad? That's a good one. And you can always do that V final plus V initial divided by 2 equals V average, which is also equal to distance over time. I think that's all of them. If anything seems missing, of course, let me know. But if you can realize that it's missing, then you probably already have it memorized, so you don't need to. You can work any of these projectile motion problems backwards. So what I mean by that is maybe I give you the range and the height and the time that it took, and then I ask you, well, what angle was it launched and what was its initial velocity? So all of these equations, of course, if I give you an equation like V final equals V initial squared, V final squared equals V initial squared plus 2ad, instead of giving you the initial velocities and final velocities and accelerations and asking you the range, I could give you the distance and say, what was the acceleration? Or, well, that's always gravity, so it's not a good example. If you know it's gravity and I give you the distance, you could find the initial velocity or the velocity that hits the ground with things like that. So be aware that this is the standard way that you'll solve the problem. This is like the easiest, most straightforward way. You're given the initial velocity and the initial angle, and then you're asked for all the other stuff. But you can always work backwards, and frequently, like in a laboratory experiment, you can measure easily how far it went, and you can time how long it was in the air. So those are things you can measure, and then you can work backwards to figure out what was the launch velocity. Because knowing the launch velocity in an experimental setting is not nearly as easy as measuring the range or timing the time. Okay, so I wanted to use this projectile motion simulator to help you gain an intuition of what these projectile motion problems look like. It'll help you get an idea of how the launch angle and the launch velocity affects the projectile, and it will help demonstrate that the mass doesn't matter. So let's just start with something simple. I'll do 5 meters per second at a 45-degree angle, and we'll shoot it. and you can see, wow, that's a pretty wimpy shot. So let's increase our speed to 10. So I doubled my speed. What do you think is going to happen to the distance? Is it going to double? Is it going to cut in half? What's going to happen? So you can actually use this little ruler right here, and you can measure. This distance was around, and I'm not looking where it landed, because it lands at a lower place than where it was launched. Remember I said we always have them land at the same place that they launched from? So this is around 2.7, and this is around 10.4. So this is actually like 4 times farther. Now let's see what happens when we change the angle. What if we put it at a steeper angle? So now it's cannon is launching more vertical. So we expect it to go higher. Will it also go farther, or will it go not as far? So it goes higher, but then it doesn't go quite as far. What if we go like to a really steep angle, like 85 degrees? Then it goes even higher, but again, much less distance. Okay, what if we go to, let's go back to 45 just to visualize again, which was 45. 45 was this one here. Sorry, you can't really see it. Let me change the projectile to a tank shell. Oh, changing the projectile, which made the mass different, had no effect. You see that? What if we shoot a bowling ball? Change the mass, change the size, right? Same projectile path. Let's shoot a football. Same projectile path. Let's shoot, oh my god, a human. Oh my god, same projectile path. Of course the guy dies when he lands. Oh, what about a piano? Same projectile path. And a Buick. Oh my goodness, same projectile path. So the mass and the diameter make no difference as long as you're ignoring air resistance, because if you're ignoring air resistance, they all experience the same acceleration, which is gravity, which is 9.8 meters per second squared. Okay, let's go back to something simple. Tank shell. So we're looking at this path. What if we decrease the angle to, say, 30 degrees? Okay, so it was a smaller, let me zoom in here. Maybe is that better? You can kind of see a little bit more what's going on. So when we shot it at 30 degrees, it was a lower angle. Let me clear. Let me just do 3. Let me do 30 degrees. There's 30. Let me do 45. And let me do 60. Something interesting is going to happen. You can see that the 30 degree angle and the 60 degree angle, they both cross the axis at the same point, which means if we weren't considering that they actually went underground here, they would land at the same distance. That's kind of cool. Same thing, let's try like 80, and then 10. They both cross at the same point there. But you can see the 80, it's in the air for a lot longer because its vertical component is a lot higher. Okay. What about shooting? Let's shoot a bowling ball. And let's make the angle back to 45 again, and let's change the speed to 15. So you can see there's 15, there's 10. Wow, what a big difference, right? So this one went a little over 10 meters. This one went like 20 something meters. So the velocity has a huge impact on both how far it goes, but also look how much higher it goes. We can try to measure the vertical height here. Vertical height 2.5 or something, and then vertical height over here is a lot higher, 5.5. So this simulator is really cool at helping you kind of visualize what kind of projectile motion will look like. You can also just drag this to anything you want and shoot it. You can, I don't know if you can set in the range. Nope, this is just this will tell you the answers. These aren't very good though, because it tells you the value like once it's gone underground, and since we're trying to consider things that are launched at the same height that they landed at the same height they were launched, it's not as good. You can also try to hit the target, I guess. That's probably what you're supposed to do, right? So too short, increase the velocity a little bit. Too big, decrease the velocity a little bit. Bullseye. I guess we score. I don't know what we score. It's pretty exciting though. Well done, Morgan. Alrighty, have fun with this. You can play if you want. It's on phet.colorado.edu, same place we had the other sims. And now we'll get back to the lesson. Okay, so take that in your mind. Projectile motion, things flying in parabolic arcs, and kind of move that to the side, or even better yet, stop watching this video, practice a couple of the homework problems, go do something else, and then come back for circular motion, because it's related in that it's two-dimensional motion, but it's kind of a different thing. So circular motion, here we go. Circular motion is one of the most common things in the entire world, and you just may not notice it because a lot of times it's only part of a circle, not the entire full circular motion that you see. So a pendulum swinging back and forth, that's actually circular motion, because if you trace it all the way around, it would form a complete circle. But so any arc that's part of a circle follows the equations and physical laws of circular motion. So swinging a pendulum, planets orbiting the sun, grandfather clocks, swinging a swing set, merry-go-rounds, a shot, not a shot, but whatever this is called, the Olympic sport. They're all around you, so it's worthwhile to understand this concept. So try to understand. I mean, this is a little bit tricky, even though most of us have probably ridden on a merry-go-round or one of these toys where if you spin it really fast, you feel like you're going to fly off, and there's something like physically pushing you outward. Our intuition actually is not very good about the forces involved in circular motion. So, okay, so let's take a look at this example. You're going to try to figure out what's going on, and we're going to use, I don't know what this is, it's not a merry-go-round, maybe it is. One of these that you spin it really fast and it feels like you're getting flung off of it. We're going to use that as an example to kind of go through these 5 questions that will help you figure out what's going on, even though it may defy your intuition. So suppose you're standing right here on the edge, and this thing is spinning around. Yes, you're a really small person, and this is spinning around at, say, 1 revolution per second. So that's actually pretty fast. So it's spinning around 1 time per second. Is your speed changing? So think about if you were standing there. Maybe pause the video if you want to think about what's going on, and then resume to get the answers. So is your speed changing? Since it's going around at 1 revolution per second, assuming that you're staying in your position here and you're not moving, then your speed is actually not changing. Your speed is just a constant value as you go around. Next question, is your direction changing? So think about if you were standing there, would the direction that you're moving change, or would it stay the same? Okay, if you're standing here, imagine you were facing this way. At one point in time, you would be looking over here. But then as this revolves around, and you're standing over here now, you'd be facing this way, and you'd be looking at something over here. So if you imagine standing on something that's spinning, what you're looking at is going to change. And so your direction is changing. Okay, so your direction is changing, your speed is not changing. Next question, is your velocity changing? Okay, we've already decided your speed is not changing, but your direction is changing. So now what about your velocity? So think about that, try to remember, okay, what is velocity? Drag it out of the depth of your memory. If you remember that velocity includes both speed and direction, if your direction is changing, then your velocity must be changing. There's no choice about it. Yes, sorry, this is not very bright color. I'll put the Y's here. So no change in speed, but yes, change in direction, which leads naturally to a change in velocity. You can't change direction without changing velocity, because velocity includes direction. Okay, move on from there. Is there an acceleration? Are you accelerating as you go around? Are you accelerating? So this one's tricky to think about. Are you accelerating? Okay, let's look at the definition of acceleration. Acceleration, remember, is a change in velocity over time. You must have that memorized, by the way, in case you don't. The definition of acceleration is a change in velocity over time. Well, we just said you have a change in velocity. So if you have a change in velocity, then you must be accelerating. There's no possible way for you to change direction without an acceleration, because that's the definition. Okay, cool. So you're definitely accelerating. Now, the real kicker, are there any forces acting on you? In order for you to stand here as this rotates around, are there any forces on you, or are you in equilibrium? So think about that. Okay, hopefully you got this one right. F equals ma, my friends. Or rather, F net. Oopsie. F net equals ma. We just said you're accelerating. Yes. Therefore, yes. There must be a force on you, right? If there was no force on you, which way would you travel? You would travel in a straight line. That's Newton's first law. If there's no forces on you, you continue to move with constant velocity in a straight line. So in order for you to have a curved path, you're not moving in a straight line. The only way that can happen is if there's a force keeping you on that curved path. Okay. So if there was no force what would happen? You would go on a straight line. So imagine here's a circular path, and you're standing right here, and your velocity is this way. If the net force was 0, you would just keep going this way, and you'd keep going this way, and you'd keep going this way, and you would definitely no longer be on the roller coaster, or the whatever this curved path is. So which way should the force point to keep it going on a circular path? So if you're going this way, and you wanted to be going this way, should the force push on you to the left, or should the force push on you to the right? Okay, hopefully that doesn't insult your intelligence. The force should be to the left. Okay, and that will make you curve off to the left. Now you're right here. Okay, so now your velocity is this way. Should the force be up, or should the force be down to keep you on this curved path? I hope you agree the force should be down. Okay, and that's going to curl you over to here. Now, you're here, you're moving this way. In order for you to keep curving this way, should the force be out that way, or should the force be in this way? I hope you agree the force should be in this way. If you're going this way, and someone's pushing you that way, you're going to end up going in between the two, curling off to the side. Okay, now you're right here, your velocity is this way. You actually want to curl off to your left. How do you curl off to the left? You have a force push you to the left. And this force was to the left, so I'll just draw it in right here. So what do these 4 force arrows have in common? They all point towards the center of the circle. In order to stay on a circular path, you got to have a force pushing you constantly towards the center of that circle. So I've drawn them just on the 2 sides and the top and bottom, but actually the force is occurring all the time, and it's pointing inward all the time. The continuous force the entire time. If you wouldn't have a continuous force, you would immediately start traveling straight instead of continuing to curl. So this is basically what I've just drawn, but a nice clean version of it. If your object is moving tangentially to the circle, which is what happens if you're standing on a merry-go-round, the needed force is directed inward towards the center of the circle. Okay, so you might be asking yourself, that seems a little weird. Whenever I stand on one of these merry-go-rounds, I feel like I'm getting thrown off, not like I'm getting pulled towards the center. And that's true. You're not getting pulled towards the center. The problem is that we're used to having what are called inertial reference frames, where things are just moving in straight lines. So if you were to be right here, if you moved in a straight line, say I was standing right here and you were on the roller coaster. If I move quote forward 10 feet, I might end up right here. So take that same length, and follow it for you. You moved this way, right? And so when you follow this curved path and I follow this straight path, it looks to you like I got thrown off out that way, doesn't it? It looks to you, relative to you, I'm perpendicularly outward, right, from you who are still on this track. So if you were to let go, you would travel in this straight line. But when you look back at your friend who didn't let go, you see him here, you don't see him over here because he's moved. And so your mind is telling you, oh my God, I got thrown off perpendicularly outward. There must be some force pushing me perpendicularly outward. Actually, there's no force on you at all. You just moved in a straight line. So it's really hard for your mind to accept what your eyes are telling you. You had 0 net force on you. When you get quote flung off of a rotating what do you call it? God, I keep losing this word in my mind. Merry-go-round. When you get quote flung off a merry-go-round, you actually didn't get flung off at all. All that happened is you went in a straight line, and it actually receded away the other direction from you. So it appears to you as if you're getting flung off, but you're really not. So in order to stay on it, you have to have a force holding you onto it as it takes that curved accelerating path, and that force points inwards. So imagine, if you were a person and you were standing on a bathroom scale right here. Never mind, ignore that. We'll talk about that later. Okay, so hopefully this makes sense so far as a concept. All right, let's talk about the actual magnitude of the force needed. So actually, I'll go back to the picture real quick. suppose you are really small. Do you think it takes more force or less force to keep you on? So if your mass is little, I think it makes sense that you have less force. Tell me if you disagree, but if something is small, it should take less force to hold it on. What if the radius of the circle gets smaller? Okay, if you made a smaller circle, this one you're making a very sharp turn, this one you're making a more gradual turn. Which takes more force? Can't talk. Which takes more force? A really sharp corner or a very gradual corner? I'm kind of leading you in with my voice, I hope. But if the radius of the circle goes down, it's a sharper corner, then you're going to need more force. And lastly, what if the velocity goes down? If you decrease the velocity, you're going slower. Well, I hope this one is pretty clear also. If you're going slower, it's not going to require as much force to turn. So this is what our intuition tells us, or this is what my intuition tells me, so hopefully yours matches, or after I've explained it, it seems reasonable to you. Let's take a look at the equation. The net force is pointing radially inward, so we already established that. And the magnitude of the force is m times v squared divided by r. So if the mass goes up, heavier object, it's going to require a bigger force. If the velocity goes up, it's going faster, it's going to require a bigger force. But the radius here is in the denominator, which means if the radius goes up, the force needed goes down. So a bigger circle takes less force. Likewise, if you decrease the radius, you make it a smaller circle, it's going to take more force because it's a sharper corner. It's a sharper turn that you're making. So this force pointing radially inward, it's perpendicular to the motion, so it's not going to speed the object up or slow the object down. It's just simply going to turn it. So if you want your object to speed or slow, you have to provide a force in the same direction it's going to speed it up, or a force in the opposite direction to the way that it's going to slow it down. And those forces would be called tangential. So if this is a circle, a force inward is a radial force, because it kind of looks like a radius, so that's a radial force, and that would be a tangential force because it's tangent to the circle. So there's a tangential force, there's a radial force. Radial force will change your direction. I'll write this, will change the direction, and a tangential force will change the speed. And of course you can have both these at the same time, right? This is two-dimensional motion. So you can have both a tangential force and a radial force acting at the same time. A fantastic example of that is a roller coaster. When you're doing loop-de-loops, your speed is changing and your direction is changing, so you've got forces making you feel heavier, like when you go around the curve you feel heavier, but also when you get to the top of it you feel lighter and you're changing speed, you're speeding up, slowing down. It's a crazy combination of these two with a twist and a twisting, and also loop-de-loops can do that. There's a lot of physics in roller coasters actually, so that's kind of an exciting application of circular motion. Let's try an example. Have any of you seen the movie Tokyo Drift? It's actually, I would recommend it, it's a pretty fun movie. But there's one scene in there where they take a car and they put a cheese grater on the front, I think front bumper, and then the guy, he drifts around in circles and he's like grating cheese out of the middle. So imagine you've got a car and it's basically going around in circles. So we're going to use the center of the mass of the car so that the bumper is actually tracing a very small circle around the cheese itself, but we're treating the center of the mass of the car as going around a circle here. So I've estimated these numbers. I don't know how well this is going to work out, but assume the center of the car is around 3 meters away. So from the center of the car to the center of the cheese is 3 meters, and the car is moving at 13 meters per second around this path. I estimated that since it seemed reasonable based on the size of the car and how long it takes to go around. And for Stuart, who's corrected me on the typical mass of cars, thank you, sir, we're going with a 2,000 kilogram car. So the first question is, what force of friction is needed between the tires and the ground? Well, ask yourself this, could a car do this on a slippery surface? No, it couldn't. The tires have to grip into the ground in order to turn, and that's a force of friction. So the force of the circle is mv squared over r. The mass is 2,000. The velocity is 13, and we're going to square that. And the radius was what, 3 meters? Okay, so let's find the force. And this is force of circular motion. Force circle, that's just like a concept. It's not an actual, there's no such thing as a circular motion force. Every force is actually applied by an object, like by friction or by gravity or by someone's pushing or pulling, like a physical contact between two things. So here I'm putting Fc for F circular, and here I'm putting F friction. And it's important that you realize or understand that the force of the circular motion is the concept. This force of friction is causing circular motion. Okay, so when you have force of circle equals mv squared over r, you're never going to plug in force of circle. You're always going to plug in some real type of force, like friction force, normal force, pushing or pulling or tension, something like that, or gravity even sometimes. So what's 2,000 times 13 squared divided by 3? Heck, I don't know. 13 squared is 170. 170 divided by 3 is roughly 60. 60 times 2,000 is roughly... This is really, really rough, so I'm not sure. Oopsie. With a comma right there. And what are my units? Those of you who don't like to put units, make sure you remember newtons. So that's the force that we need to apply in order to keep this car on the ground. And then second question, let's make it a little more complex for ourselves. What's the coefficient of friction? Well, luckily we have a formula for this. Force of friction equals mu F normal. So now we can look at this car from the side, and we can say that F normal is up, F gravity is down, and if it's kind of going around in this circular path, the force of friction is pointing inward towards the center, making sure it stays on track. So this is like a top-down view, and this is kind of like a three-dimensional or side view of the car. So like here's the car's wheels. Maybe it's whatever. There's your car, forces inwards. So because it's on flat ground, it hasn't told us that, but we're assuming it's on flat ground, the normal force is equal and opposite to the force of gravity. So force of gravity is mg, so the normal force is mg. So force of friction, we just figured out was 1,200. No, sorry, 120,000 right there. And we got to put in our mu. The mass is 2,000 kilos, and normal force is mg in this case because it's on flat ground, so 9.8. So let's solve for mu. So we can do 120,000 divided by 2,000. Cross out 3 zeros. Cross out 3 zeros. 120 divided by 2 is 60. 60 divided by 10 is 6. So mu is a roughly 6. I'll be honest with you. That seems way too high to me. Realistically, I don't think the coefficient of friction between rubber tires and the ground is 6. But that could be because my estimates for the velocity that you could attain are incorrect. Likely, maybe you can't actually go quite this fast. If you tried to go this fast, you could never turn this sharply without flipping the car over, probably. So maybe the velocity should be a lower estimate. So I apologize that maybe the numbers didn't come out quite as well as I would have hoped, but I hope that this illustrates the concept of circular motion, how to find the forces involved, how the mass, velocity, and radius influence the forces involved, and also a small application involving friction to remind us how to do that. Okay, so just like I said before, take a break in between the projectile motion and the circular motion sections. You're welcome to take a small break or go do something else, or if you have no time, this is a perfect stopping point because our third topic for this lecture is called relative motion. It's actually probably easier than the first two examples, but that doesn't make it any less important. So whenever you're ready, go ahead and continue. Relative motion. You can do relative motion 1D examples, which is just like motion is constrained either up and down or side to side. So this is like you could be in a train, and the train is going forward, and then you're in the train and you're walking forward or you're walking backward. Your actual velocity relative to the outside world is a combination of your affected velocity relative to the train and then the train relative to the outside world. So it's a combination of the two things that are moving. Going on a treadmill is another example. That's a pretty poor example. I'm not sure why I put that. Unless the treadmill is moving, well, I guess it's an okay example. You're walking forward while the track is going backwards, and so whatever your forward velocity is, assuming the treadmill is stationary, must equal the backward velocity of the track, and so they can measure the RPMs of the track and how long it is, and then they can tell you what your speed is on a treadmill. So maybe it's a lesson in how a treadmill calculates your velocity, assuming it's at rest. The 2D examples are a lot more interesting and also a little bit more mathematically complex. So anything where your speed is one way and there's a cross-directional force on you. So if you fly a plane with a headwind or tailwind, you're going in one dimension. But if you fly a plane and there's a crosswind coming in, that's going to push you off course. So it's going to now be a vector where you have vector components that are not lining up. Another one is boating across a river. So here's a little nice picture. Maybe the river is going, downstream to the right, but you need to boat yourself across. If you point the nose of your boat straight across, you're going to kind of veer off and you're going to go sideways. So if you wanted to go straight across, you actually have to face your boat upstream so that you're paddling upstream, but the stream is pushing you down, and the combination of that might take you straight across. So it depends what you want to accomplish. But you can take into consideration both the motion of you relative to the medium plus the medium relative to the Earth, and find out how fast you're actually going relative to the Earth. So this method will work for all problems, whether it's airplanes or boats or people on trains. Add them as vectors. That means direction is critically important. So the velocity of u relative to the object plus the velocity of the object relative to the outside world equals your total velocity. So if these are both going the same direction, you add them, and your actual velocity is faster than it would have otherwise been. If these are going opposite directions, you subtract them, and your actual velocity is less than it would have been. If you have multiple directions, then you have to break them into components. So I'll write this again, even though I've said it a million times. Always, always, always break vectors into components using sine and cosine. Those which you are very good at by now. So that's a pretty terrible. I tried to do it in cursive, without unclicking the mouse. Break vectors into components. Draw a picture, calculate values. Let's do 2 example problems, and then we will be done with this lecture. And you can go on and start the homework. You walk south at 2 meters per second on a train moving north at 8 meters per second. So let me first define this as north and this as south. Let me put a train going 8 meters per second, and let me put u going 2 meters per second. So if we define north as positive and south as negative, this one is a positive 8, this one is a negative 2. So your velocity total is your velocity, which is negative 2, plus the external velocity of the object that you're in, which is 8. So your velocity is obviously 6 meters per second. So, I think you could have all gotten that in 3 seconds just by looking at the problem, but it's nice to sometimes visualize it, set up an easy one following the rules that you've seen, and then verify, okay, everything works out the way it should. Okay, now a little bit harder, 2-dimensional problem. You can row at a speed of 4 meters per second in still water. So you try to row directly across a river that flows at 90 meters per second. What is your actual speed and direction in the water? Let's draw the river. Let's say that the water is flowing this way at 9 meters per second. So you try to row directly across, which means you're trying to go this way. And how fast can you row in still water? You could have gone 4 meters per second if the river was not flowing. So you're going 4 meters per second this way, and the river is pushing or carrying you 9 meters per second this way. So which way will you actually go? You're going this way at the same time as you're going sideways, and so you're going to go at a diagonal. This is vector addition. So remember we learned the tip to tail method? You can imagine putting this guy right there. So your actual velocity is going to be this way. So this is your v total. It's vector addition, a vector addition of these two guys. Since they're perpendicular, it's pretty simple. You can use Pythagorean theorem to find this. So this side is 4, this side is 9. So v total, Pythagorean theorem, remember, is going to be 9 squared plus 4 squared. Square this base, add them together, and then square root. So 81 plus 16 is 97, so you got the square root of 97. meters per second. So you're looking at roughly 10 meters per second. So you're going a little bit faster. Obviously, the hypotenuse is always longer than either of the two legs. And the other question says not only what is your actual speed, square root of 97, but what is your direction? So you're not going directly across. So let's find this angle here. We know the opposite and we know the adjacent, so we can use tangent inverse of, tangent inverse of opposite over adjacent is 4 over 9 to get our angle, and I honestly have no idea what that angle is. So you're going to have to use your calculator and get the angle. I can tell you one thing for sure, it's less than 45 degrees because this side is smaller than this side. So always use common sense check like that when you're doing tangent inverse on a calculator or finding any angle for that matter. You can always tell if it's less than 45 or greater than 45 based on these two sides, right? If this side is smaller, then this angle is smaller. If this side is bigger, then this angle here is going to be the bigger angle. So calculate some angle less than 45 degrees, and that's your heading. If I told you the distance across the river, then I could ask you how far downstream you went. To do that, you would make similar triangles. Like, if you go up 4 and over 9, then you can make that like this ratio 4 over 9 equals distance across over distance downstream. Things like that. You can do all kinds of geometry. But if we haven't done that in class, then the only way it would be asked would be a level 3 question. But just be aware that there's some cool stuff you can do with flying off course or rivers and whatnot. Alright, I hope you found this video helpful and informative, and now you can start the homework, work through it. On Tuesday we'll go over all the homework problems plus concepts and stuff that you guys have questions with when watching the video.